Okay, so make sure I don't forget to record this one. So yeah, now the point here is, right, we're trying to, and this is where they're asking you to find discontinuities and tell what kind of discontinuities they are, right? Okay, the point that's being made here is that finding discontinuities is really just a matter of looking for places, even within functions of functions, compositions where things blow up. Now this is a composition, isn't it? Right? We've got an outer layer and an inside layer. We've got, on the outside, we've got e to something. And then on the inside, it's actually e to the 4 over x. So there's a function within a function here. The natural, or the exponential function is defined everywhere, isn't it? Right? If you think back to last year or to Honors Algebra 2, you think back to when you were talking about exponentials. Didn't they just look like this? Right? We just did that, right? And so there's no place on there where we're getting vertical asymptotes or holes or anything. They're continuous and defined everywhere, right? So that's fine, except within the argument of that exponential, we have an inverse function, right? And that could cause problems, okay? And so I think, in your minds, I think what we're getting at with this problem is, well, I know what we're getting at, is this, just to train yourselves to think, even though this exponential may be okay, if there's a part that's trying to feed the exponential numbers, and that's all that interior function's doing, right? That inside function is just we're plugging inputs in for x and it's spitting outputs, and the outputs become the inputs for the next layer of function, for the exponential. But if the inside function is unable to spit out numbers for the outside function, it still is undefined then, right? Does that make sense? So there's still a red flag that goes up. So where is this thing going to be undefined?
Yeah.
At 0, yeah. Yeah, because at 0, the interior function is undefined, right? Does that make sense? Okay, what kind of a discontinuity is that going to be? Yeah, it's going to be infinite, isn't it? Yeah. Does that make sense? That's all they're getting at. Now we could look at that graphically, and all we're going to see then is as x approaches 4, we're just going to see this big spike in the function because the outputs are going to become infinite. Okay. All right. Other questions? That's a good one. Anything else? Okay. And then we can deal with those mainly in the lab. But if there's any, it's a good place. If a lot of people are having issues with something, here's a good place to do it. Okay. What I want to do today, I want to just take another step forward. What do you think about this? We're going to look at we're going to talk about infinity a little bit today. We're going to talk about limits involving infinity. Okay. And we've always said, up till now, we haven't had a real long history in calculus yet, but we've always said that when we have functions like this, f of x equals something like 1 over the quantity x minus 1 squared, if we take a limit of that as x approaches 1, that was one of our 3 kinds of answers, right? That was the kind where we got a number on top and a 0 on the bottom, and we just said no limit. Now, it makes sense that we said that. And let's just review real quick, why does that make so much sense? Well, if we go back to our formal definition of a limit, which, I want to use this opportunity to just dredge this up one more time, because we don't get to look at this very often, but this is important. Remember this? Mm-hmm. This thing we talked about where we said that in order for us to really be able to talk about something as a limit, it has to have this, there has to be this relationship between the width of what we call the neighborhood, right? We define that with this quantity delta. How close are we getting to our x value? The ant's walking along the function towards an x value of c, and the idea is that depending how close he gets to that value of c, he will get arbitrarily close to his target value, or the value of y that he thinks he's going to step on, right? I think I just said that in kind of a confusing way. Let me restate that. So if the ant needs to know accurately what y value does he anticipate stepping on, depending on how accurately we tell him he needs to know that, he could always reach that accuracy just by getting closer to c. Does that make sense? The width of the neighborhood of values around c, x equals c, is going to be related to the width of the values of epsilon around the limit that he thinks he's going to approach. And if we tell him he's gotta be within 1/1,000,000th we gotta know within 1/1,000,000th, what's the Y value he's gonna step on, he might think, oh my gosh, that's pretty accurate. But all he's gotta do is just take some little bitty ant steps closer to C, and he'll get there, right? He'll eventually be able to tell us an answer that's that accurate. There's no limit we could ever place on him that he couldn't reach by just taking some little bitty ant steps towards x equals C. If that behavior's true, it's a limit, okay? If the function becomes arbitrarily close to a single Y value, L, as x approaches C from either side, yeah, it's a limit. Now that doesn't work here in this case though, does it? The one that we're currently talking about. If we look at something like this, it doesn't work. If we want to know what Y value does the ant think he's going to approach, the closer he gets to, well, whatever we're going to call it, 1 in this case, right? X equals 1, the more ridiculously fast the function is blowing up, and so he's never approaching a single value, right? This is clearly no limit. There is no limit. But the question I have for you today is, can we do better than that, than just saying no limit? Because our goal here ultimately is to be descriptive of the function, right? We want to be able to say something meaningful about the function. And just because there's no limit doesn't mean that it's not an important function and that we can't describe it in a way that's useful. So what do you think? Anybody have a suggestion how we could improve on that? You might be looking for something very profound. This would be a pretty simple answer. What could I fill in the box there that would be a better answer than no limit? I know you're going to get this, so I'll give you a second. There's no question you'll get this one. And just look at the shape of the graph. What's going on? As x approaches 1. Say it again. Yeah.
Oh.
That's it. That's the answer. Positive infinity. But that's important, isn't it? Because that's telling us that he's walking uphill forever, right? And from either direction, right? We just said as x approaches 1, we didn't specify. As x approaches 1, this ant is climbing an infinite mountain. Well, that's vastly different from an infinite valley, right? Because we could think of another function. If I just made the top negative, for example, this thing would have plunged down instead of going up. That's very different behavior. We might want to know which of those things is going on. Well, no limit doesn't tell us, but that does, right? Does that make sense? Okay. So to do that, though, we sort of relied on this graph, didn't we? Let's see if we can think of this in a way that's not going to rely on us. If we can come up with some kind of a mechanism or a notation that will allow us to do this algebraically without having to draw the graph. Okay, so let's try that again. Oops. Oh, I did do that. Okay, so as x approaches 1, what is the quantity x minus 1 squared approaching? It's approaching 0, you're right. It's approaching 0, but it's never going to actually be 0, right? It's always going to be small and very, very small. What's the sign of the number always going to be? Okay, if it weren't for the square, maybe, but because it's being squared, that ensures that the answer is always positive, right? So we could, and this is a little bit hokey, and you got to take this a little bit with a grain of salt. This is not meant to represent an exact solution, but more kind of a tendency, right? So we might write something like this. And what do you suppose that means, 0 plus?
Doing 0 is always positive?
Yeah, it means really small. So it's approaching 0. It's as small as you want it to be, but it's still a number, and it's still positive, right? And if we ever have, here's how we kind of look at this. If I ever have a vanishingly small number on the bottom and a constant on the top, that's telling us infinity, right? So if I sort of color code this, I could say that this part right here, the blue part, the 1 over the 0, is is telling us explosive. It's telling us the infinity part. But we still haven't filled in the sign of the infinity. Okay, that's coming from the fact that we're dividing a positive by a positive. Does that make sense? Okay. So it's positive infinity. I could change this. If I had had a negative sign on the top, it would have been different. All right, if I took the limit of -1 over x minus 1 squared as x approaches 1, I still would have gotten my 1 over 0, which would give me my infinity. But now the fact that it's a -1 over a positive 0, my sign rules tell me that that's got to be a negative answer. Okay? All right, so let's move on with this crazy idea. What if we have instead something like this? Now, if we draw the graph of that, we'll cheat for a second. Then we'll talk about maybe ways we wouldn't have to cheat. If we were to graph this, it would look like this. Oops, that's supposed to be, the asymptote's at 1, not 0 though, right? That makes sense. But it's good, but the important thing is it's a split function like this. Okay, so that one truly is, there is no single limit, but we still might be able to do better than that, right? We still maybe can do better than just saying no limit. And there isn't a single limit here like there was before. But we still might want to know that when we approach from the left, the ant's going down, and when we approach this from the right, he's going up. Suggestions? How could we evoke that behavior? Think to what we talked about yesterday. Anything that might be helpful there. And you see the point I'm making, right? On this last example, or if we had drawn one down, even though it's no limit, we can see here very clearly that the answer to that limit is infinity or negative infinity. Now this one's not like that. It's a combination of both. Go ahead, I interrupted you. Who's?
You just do the parenthesis, negative infinity, positive. You do that?
Well, okay, maybe. You're talking about the domain?
Yeah.
So the domain of this thing would be what? It's all real numbers except, what's the one value I can't? Okay, I can't use 1. That's, you could take that argument. There's something about the domain that might be useful. Yeah, so let me write down the domain while you guys are thinking. That's an idea. So the domain would be something like this. Right? There's that interruption at 1. Yeah, that's a good hint. Anything else we can do to try to get the idea? We want to mathematically pull out the idea that we're going to get this downward behavior from the left and this upward behavior from the right.
So it'd be like a negative infinity with that negative on the top and comma positive infinity.
Okay, yeah, remember we had that notation yesterday where we talked about limits where we could approach a number and then we put that little positive or negative. And what did that mean?
From the left to right.
From the right or from the left. So now we're kind of onto the right idea, right? So what if we approached 1 from the left? Okay, so we take the limit. Now how would I write that? The limit of my function, 1 over x minus 1, as x approaches 1 minus, right? Now we're specifying that we're approaching from the left. We can see from the graph, what's the answer that we're expecting to get? Negative infinity. Okay, how are we going to get that? Well, let's look. Okay, on the top I've got 1. Now look at the bottom here. This is you got to really sure, put your thinking caps on for this. If x is approaching 1 from the left, if I make that substitution, I'm gonna do something like direct evaluation here. I'm gonna get, in that case, something like 1 minus 1. What in the world? What is that gonna equal? What does that mean? 1 minus 1. Somebody articulate that in words. What's that saying? Is this number actually 1?
No.
Very close, but it's not exactly 1. It's slightly more or less than 1.
Closer.
Slightly less. So what are you gonna get if I take a number slightly less than 1 and subtract exactly 1 from it?
Negative.
Ah, very slightly negative. So how would I write that, you suppose? What is this gonna become on the bottom? Say it again.
Negative.
0 minus. Yeah, that becomes a 0 minus, doesn't it? Does that make sense? Okay. And what is 1 over 0 minus? Let's take that into the pieces. First, let's just look at the big numbers. A number over 0 tells us what?
Undefined. No.
Yeah, infinity of some kind, right? We just don't know what kind. So it's gonna equal, we know that it's some flavor of infinity. Now we gotta be specific. Just go to the sign rules. Positive 1 divided by a negative number, albeit small, is what sign? Negative. We got it. It's negative infinity.
Okay.
Right? See how that works?
Yeah.
Okay?
Yeah.
And so, let's do the same thing from the other side. Right? If we do this, the limit of 1 over x minus 1, as x approaches 1 from the right, if I directly evaluate, it's going to look a little weird. I get 1 over x is approaching 1 plus. Make sure that's a superscript. Minus 1. And what's that going to be? A number slightly more or less?
More.
Slightly more than 1? Minus exactly 1 is 0 plus. And so in 2 parts, that gives us a number over 0 explodes. What kind of explosion? Well, it's positive divided by positive. It's positive. Right? And so we got our answers. Okay? Yeah, strange, huh? Okay. Good. Okay, and I would argue when you're doing your work here on these things, this step right here, I think is really, probably we can skip that one. I think, don't you think that, like, now that we've got the idea, we could just go from there straight to there?
Yeah.
Right?
Yeah.
Does that make sense?
Yep, I'm
Okay.
being it.
All right, what I want to do, I want to look at an example. So a lot of the questions you're going to get on this assignment are going to be things where you're going to be taking rational functions, and you're going to be evaluating limits. You're going to do stuff like this, but you're also going to answer the question, whole versus asymptote, or whole versus, removable versus non-removable. So let's just make sure, and this isn't a really tough issue to resolve, but let's just make sure that we understand how that works. Okay, so I want to know on this one, any places, any points of discontinuity?
3.
3. Okay, so x cannot equal 3. Every place else is fine, right? Whole or asymptote, removable or non-removable? And how do you know?
Because that's 1 over 0.
Say it again.
Because that'd be 1 over 0.
Okay, so it's a vertical asymptote. Okay, because if I evaluate this directly, if I take a limit, even though it's undefined, the function doesn't exist there, if I take a limit, the limit of my function as x approaches 3 is 1 over 0, which tells us vertical asymptote, so it's no limit. Okay, this is a removable or non-removable discontinuity. If I wanted to know exactly what kind, I could find out, right? If I want to know what's going on, I could take limits as x approaches 3 from the left or the right and determine, what is actually going on here, right? And that's the stuff we just did. If I take the limit, we'll just do one of those, how about? Let's take the limit as x approaches 3 from the right. So what am I going to get there? I'm going to get, obviously, infinity, some kind of infinity. What's the sign going to be? Positive 1 over positive 2 times 0
Positive.
plus. Yeah, so it's going to, everything's positive, right? So I get a positive infinity. Okay? Okay, same question. I want to know, discuss the continuity of this function now. Okay, any place where, first question is, any place where it's discontinuous with functions of parts. What do you think? You seeing, Leighton, what are you seeing? Okay? Okay. What about, you're right, but tell me why. What about that on the bottom? How come I got X's and 1's there and stuff? How come I can't have a problem on the bottom? Okay, good. Because the x squared, we would say, is always going to be non-negative, isn't it? Right? It's non-negative value, no matter what. It could be 0, but it can't be negative, and so therefore, if I'm adding 1, the bottom is always positive. It's fine. That's everywhere continuous. No issues. Okay? That's 5 years. Okay, 1. Discontinuous at 1. Anyplace else?
Negative 1.
-1. Good. How do we get that again? Remember the other day? Where's our red flag?
Minus.
Yeah, right there, right? And so that stuff can't equal 0. And so if we solve that not equal to equation, find all the solutions of that, those are going to be the discontinuities, right? So x squared cannot equal 1, therefore x cannot equal plus or minus 1, right? Okay, now so we got there's our domain. We found the discontinuities. What flavors of discontinuities are those? Removable or non-removable?
Non-removable.
Okay, non-removable, they are, good. And reason being, if I evaluate this function directly, aren't I always gonna get a number on the top and 0 on the bottom at those 2 places?
Yeah.
Right? So we know that they're asymptotes, we know it's non-removable, right? And if we wanted to, we could figure out, by using our one-sided limits, what's going on. Let's just do one example. There's a bunch we could do, we'll just do one quick one. What if we do the limit of our function as x approaches -1 from the right? Okay, take a second, put your groups and see if you can make some sense of that one. We'll talk about it in just a moment. Okay, ideas? What are we going to get on top? As x approaches -1 from the positive side. So give me an example of a decimal number that might be.
0.5.
Negative
-0.5.
No, I mean, okay, yeah, but we wanna get closer.
Point nine.
negative
Point 9099?
Yeah.
Negative point 0.999, something like that. Okay, that would work, sure. Okay, so think negative 0.099999, right? Because on a number line, we're just walking backwards towards -1, right? So what's that gonna give us on the top? Something like 2, right?
Yeah.
There's no problem. Now, do you see the difference there? I don't need to have any fancy subscripts or anything on the top. I mean, if I can just evaluate directly on the top and get a number answer, can I? Right? That's just gonna be on the top. 2. There's no question about the sign of 2. 2 is positive for sure. What about the bottom? X squared is gonna be what? If I'm taking something that's like negative 0.99999 and squaring it, what's that gonna give me? It's gonna give me positive, right?
Yeah.
Is it gonna be, okay, but +1, but it's gonna be less than or greater than 1? Slightly more or slightly less than 1?
Less.
Slightly less, isn't it? Right? Because if I've got -1 plus squared, if you think about it, becomes +1 minus. Right?
Yeah.
Okay, and that we probably can deal with pretty easily. What's 1 minus? Minus 1.
0 minus.
0 minus. Yeah, good, because I'm subtracting 1 from something slightly less than 1. And so now we've got it resolved. +2 over 0 minus, we know it's infinity. What's the sign gonna be?
Negative.
Negative. You got it. Okay, good. Now, I know this, I'm probably wondering why I'm doing so many of these, but I want to hit one more, because there's a different look you're gonna see. I want you just to make sure, before you get into your assignment, that the ship is sailing on course here. Let's try this one. Okay?
Like it.
I want to know the continuity of that function, discuss continuity. So in other words, by that I mean, where are the points of discontinuity? Pretty boring, it's continuous everywhere, at least for this conversation. 2? Or
Negative
2. At the places where x squared equals 4, which would be plus or minus 2, we're going to get discontinuities. So those are the places we've got to check, right? Does that make sense? Okay, so we're going to see if we can come up with, here's our goal for this problem. We're going to see if we can come up with a strategy for doing this quickly. Okay, so we would want to we could take limits, right? And see what's going on in those places. If I take the limit of x squared plus 2x minus 8 over x squared minus 4, as let's say as x approaches +2, what's going to happen? Okay, on the bottom I definitely get 0. On the top I get 0 also, don't I? Okay, so that one's 0 over 0. Okay, is that going to be therefore removable or non-removable? Removable, right? 0 over 0 means full. Okay, so that is removable, and that's useful to know. Now, if I wanted to explore what kind of removable well, if I wanted to, okay, but that one's pretty easy, right? I know the answer, it's strike that. There's not a lot of extra exploration I need to do there, is there? It's a removable discontinuity. I might want to go further with that and actually find out what the value of the function is, but I didn't ask you that. That's the stuff we talked about a couple sections ago where we could just factor it, right, and do more work to find that limit, right? But I didn't ask you about that. I just wanted to know what's the state of the continuity of this function? Where is it discontinuous and what types of discontinuities? Let's try the other one. Limit of our function as x approaches -2. What's going on with that one? I'm gonna get 0 on the bottom, clearly, good.
You agree on top?
And on top, I'm getting
-8.
-8, okay? So, removable or non-removable?
Non-removable.
Non-removable. Now, to find those, I would have to weed through doing this limit stuff we just did, right? Approach -2 from the left and approach it from the right. That's gonna be just a little bit cumbersome because I've got all these terms to deal with, right? Is there a suggestion here? Could we have done something to this rational function initially that might have made this whole process a little easier? Yeah, what if we factored it? Right, what if we'd taken this thing and said, okay, I could rewrite this, oops, that's back. Let's see. It's equal to the limit of what? We can choose our limit later. What's the top gonna factor into?
X plus 4. X minus 2.
Bottom?
X plus 2. X minus 2.
Okay, that's pretty useful, right? Because now, right away, we can see that at x equals 2, we're gonna get a 0 over 0. Everybody see that? So right away, we know that because algebraically, those terms cancel, that's telling us that x equals 2 is a whole. Okay. It also helps us out because now when we want to look at our other discontinuity, when x approaches -2, right? By factoring the bottom, we found the zeros of the bottom, and those are going to be the discontinuities. Now we can consider an easier limit when we want to explore the other discontinuity. That's much easier to deal with than that is, isn't it? When we're approaching -2 from the left and the right. Agreed?
Yes.
Right, so now we can see here that, yeah, it's telling us that x equals -2 is a vertical asymptote, but it's also helping us because if we were to approach, let's say, -2 from the left, that's easy to do right there, isn't it? Right, if I approach -2 from the left, that's just giving us an answer of 2 on the top. -2 plus 4 is just plain old +2. On the bottom, -2 from the left is like -2 point something plus 2. Isn't that 0 negative? Right? And so now we know that from the left we're getting -infinity. And then we could easily see that from the right, so like -1.999 kind of thing, we're going to get 2 over 0 plus, which is positive infinity, right? And so, yeah, I mean, I know I spent a lot of time on this, but I just, I'm just convinced that being good at calculus is not just about knowing the calculus, it's about knowing how to be efficient with it and come up with, you be very systematic, because it gets a lot harder down the road. And if you prepare yourself to deal with that systematically, it always pays off. Okay, being as we're almost at the end here, I got one last thing, the kind of a review point I want to show you. What would you do about something like, what would you do about something like this? Because this is, you're going to see stuff like this. What if I give you a different function? I want you to, and there's lots of good answers. I want you to discuss the continuity of this function. So let's have a little discussion about that. What's problematic about this one?
The cube.
Yeah, I got a cubic polynomial on the bottom, right? In order to find the discontinuities, I have to know the zeros of the denominator, and it's a cubic, and so that's a little harder to do, right? If it was a quadratic, we're absolutely set.
Oh, yeah.
If it doesn't factor, what can we always do to find the zeros? If it's a quadratic expression. quadratic formula. I mean, I have an ace in the hole, right? There's always a quadratic formula to find the zeros of a quadratic expression. Always gonna work, even if it doesn't factor like all of our nice convenient ones have. There is no cubic formula. So what do you have to do here? Well, you gotta find the zeros of that cubic. Now, it used to be that we spent a lot of time in pre-calculus and analysis, in elementary analysis, talking about how to find zeros of polynomials using these techniques of, rational root theorem, and you probably talked about that stuff a little bit. But we don't do that so much anymore, because practically speaking, if I just said, anything's fair game, solve that, what would you do? Yeah, you use a graphing calculator, right? You use a graphing calculator, and at least maybe you just would find the zeros of that denominator on a graphing calculator. And that's something that I want you to understand. That's good. That's what you do. In real life, when you're doing math, like my background's in physics, I just went right to the calculator. I needed to know the zeros. I didn't really need to spend a lot of time finding them. And that's a great tool for doing that. Does everybody have on their graphing calculators a tool for finding zeros of polynomials easily? Because if you don't, that's something I want you to have. I've got one for you. So just look real quick. Like, I know you guys frequently use Aqueduct. Is that the one you use? There's another one too called PolySmlt 2. It's a horrible name, but it's a great program. It's actually a TI program. It's a polynomial solver, and it does some other things too. Go under apps and see if you don't have that one. Next time we're in the lab, let me give that one to you. It's a good one. Yes, you have that one? Everybody, this is the one you can check for.
Oh, no, I don't have it. No, I don't have that.
Oh, yeah.
PolySmlt 2?
No. No.
Okay, raise your hand if you don't have that one.
Oh, I don't have that.
Okay, so next time we're in the lab, I'll just bring some cables down and we'll make sure we set you up with those. Well, the other thing is too, while we're at it, while we're talking, because I'll forget, check your operating system. So you want to have the most updated operating system. All you do is go to, memory, or no, I gotta look on the screen. To check it, you just go second, memory, about. It'll tell you the operating system. You want to have 2.55 MB.
Yeah, where's memory?
Does anybody?
Plus?
Yeah, plus 7. So second,
GI 84.
memory, second plus, then just hit enter. You should have 2.55 MPs. Anybody not have that? A couple people? Okay, so once again, when we're down there next time, we'll load you up with the new system. Okay, so we got some ways to do that, right? We can find the zeros. With technology. Just quick review though. What if on the AP test or on what if you had to do this problem without a calculator? How could we maybe try to deal with this? I don't know if we're gonna get this in or not, but we'll try.
Try to group it.
It's gonna be, now first of all, it's gonna be pretty hard if the roots are irrational, forget it. But you're never gonna get that problem either. That's just too hard a problem. You're never gonna get one like that. So, unless it's, some product of quadratic expressions that's easy to factor, but this isn't. How would we approach this one without the benefit of our calculators? And there's a bunch of ways we can do this.
Group it.
Okay, good. I'm glad everybody saw that. We could factor this by grouping, couldn't we? Right, so let's look at that real quick. I'm gonna build in a little review here. So we could take the denominator, and people recognize right away, and what's you tell me, those of you who saw grouping, what's the signature there that gave it away? What told you? Okay, good, because we saw a ratio of 1 to 2 and 1 to 2, right? Okay, and that told us we could group this thing. Quickly, let's look at that. If I break this, just the denominator, if I break that into 2 groups. Now here's something else. You may do this, but I want to make sure you do this correctly. You always want to have a plus sign in the middle when you're grouping. Okay. Sometimes books will show that with a minus sign if this term's negative. That's a bad idea. It's always better to put a plus sign there. Okay, so that's what we do, and now we just take each of those 2 terms, and we're just going to group them, right? And we'll start with the left, and we'll break this up. What do we always do with grouping? We break out the
Common term,
Say it again.
common term,
The greatest common
Yeah.
factor.
factor,
So we'll pull out, what is that for the
x
first
squared,
group?
x
Okay, so we're gonna pull out an x squared, and then what I call the leftover factor is what?
x plus 2,
Okay, I just wanna make sure everybody's, 'cause I didn't teach this to you, and I've got a very specific way I like to do this. I'm pretty anal about certain things in math, and this is one of them. When you're doing grouping, there's a process that makes this easy. You know that if this thing is gonna group, and you already know it is gonna group, but what if you didn't? You're just testing. If it's gonna group, you know that you have to get the same leftover there, don't you? You have to. Is this the way you were kind of taught to do this? So you immediately just write that leftover term there, and then ask yourself the question, does it work? Can I pull out a GCF to make that work? Yeah, I just pull out a 1, right? In this case, right? Okay, and then now we're set. So we know that we've got this common leftover factor that I can extract from both of the two terms. So I get my x plus 2 times what's left over? Well, x squared plus 1. Whoops. Is that looking familiar? Okay, and now it's down to a place where we can deal with things. Okay, that's good. That's good. What if, because it's possible, what if it doesn't factor by grouping? So now we're still trying to find the zeros of, what's our denominator? X cubed plus 2x squared plus x plus 2. I better go to the next page because I'm going to run out. Oh, that's huge. Okay, how else could I do that? How could I test for zeros? I could not put 0 in, but I want to get back, if I'm testing for zeros, right, I should be able to, by the zero remainder theorem, not that we care about that, but I should be able to get a result back when of 0 when I evaluate this expression at x equals some number, right? If I get back 0, then that x value is a 0, right? So there is a trick for that. We could use synthetic substitution. Remember that? Right? So if I have to count for all coefficients, including zeros, right? And I've got, this is a cubic function, so I know I'm going to have 3 plus the constant, so 4 terms. So I got to write my 4 coefficients down. 1, 2, 1, 2. And if I get a 0 in the box, it's a 0, right? And I can just keep running numbers through that. Now, you might want to not use huge numbers, obviously. And in this case, would I probably want to pick positives or negatives? Thinking about the synthetic process, whatever number I seed this with out here, I'm going to multiply and add. So what's the problem if I pick a positive number? It's going to keep going up, right? Because all these terms are positive. Does that make sense? And I'm just kind of thinking out loud here. So I want to try something negative. Let's try like -2 or -1 or something. What if we try -2? Okay, if I try -2, I drop the 1 down. -2 times 1 is, I add synthetically, opposite of long division, right? So I get a 0, 0, 1, -2, and I got it, right? Okay, is that us? Well, I guess we got there. I just wanted to fill in as much review as I could with the last little bit of time, but you got the idea. Tomorrow we'll be in the lab.